we have talked about collisions already, and we just have a couple pieces left that would really be helpful. One is the idea of an elastic versus an inelastic collision. Another one coming up is just collisions in multiple dimensions, which is going to be a little bit easier than it sounds. So first, elastic versus inelastic collisions. Okay, let's say I have a block like this. Mass 1 will give this thing 8 kilograms, and we'll have it move at 5 meters per second. And it's going to run into a second block. The second block will give 2 kilograms. And we can say this one is moving at, we can even say to the left. We can say that's 5 meters per second also. After the collision, let's say they stick together. Now I've got, with this, a whole lot of momentum to the right, a little momentum to the left. So I know I'm going to end up with momentum to the right. And we can figure this out. Our initial momentum is going to be 8 kilograms times 5 meters per second. I'm calling to the right my positive direction. So plus 2 kilograms times negative 5 meters per second. 8 times 5 is 40, 2 times 5 is 10. This is negative 40 minus 10, that is 30 kilogram meters per second. My final momentum, I've got 10 kilograms times V final. My initial has to be equal to my final, so 30 is 10 times V final. My V final is going to be 3 meters per second. And that's good. That gets me to my final energy, or my final speed, which is something that I am interested in. Let's see how the energy is affected in this, and I'm going to do this one in blue. So my initial energy, it's all kinetic. We're not talking about doing this uphill or anything like that. I'm going to have a half m1 v1 squared, a half m2 v2 squared. So a half 8 kilograms, 25 meters, 5 meters per second squared, and a half 2 kilograms. I guess I've got a velocity of negative 5 meters per second, but I'm going to square it anyway. I'm only worried about the speed. 5 squared is 25 times half of 8, so 25 times 4, that's 100 joules. 5 squared is 25 times 1 is 25 joules. I have 125 total joules of energy to start with. In the end, I have a half of now 10 kilograms times 3 meters per second squared. 3 squared is 9 times half of 10, so 9 times 5, that's 45. 45 joules. I'm down 80 joules. And there is a very obvious question to ask here of, what? Where did my energy go? It can't disappear. Where did it go? There is energy that's required to hold items together. So there is a certain amount of potential energy that is built up in that way. Or if you have, for example, 2 cars that collide, the cars crumble, right? Like they kind of get mangled. They don't stay particularly rigid. So if they're going to kind of mangle, if they're going to deform, there's energy that goes into that. There's a whole lot of noise. There's heat. There's energy that goes into that. When these things stick together, we are going to lose energy. Anytime that we are losing energy in a collision, that makes it an inelastic collision. And this is inelastic because delta E is not equal to 0. We have lost some energy that makes this an inelastic collision. Every collision where things stick together will be inelastic 100% of the time. But now let's look at what happens when things don't stick together. I'm going to start right back up with my same situation. Mass 1 is going to be 8 kilograms. This thing is going to be moving 5 meters per second. Mass 2 can be 2 kilograms. And it can be moving at 5 meters per second to the left. We'll still call it to the right, the positive direction. Now first we said, let's have these things stick together. Now, let's have them not stick together. Let's see what else we can do. What if after the collision, this thing is still moving to the right? And that would happen, right? If this were a bowling ball and this were a ping pong ball, and they ran into each other, then that bowling ball's not exactly going to be turned back. So this is possible. If this thing's still going to the right, then this thing is going to the right. It can't really go through it. So we'll do our momentum calculation. Our initial momentum here, 8 kilograms, 5 meters per second, plus 2 kilograms, negative 5 meters per second, is still going to be 30 kilogram meters per second. Over here, our final momentum has to be 30 kilogram meters per second, but we're going to have an 8 kilograms times a 2 meters per second plus 2 kilograms times V2. 8 times 2, that's 16. So I've got 30 equals 16 plus 2 times V final. V final will be, we've got 30 minus 16, that's 14, over 2, and that is 7 meters per second. So we can figure that out. And now we're going to look at the energy. The energy initial is half 8 kilograms, 5 meters per second squared, half 2 kilograms, negative 5 meters per second squared. That's still 100 joules. That's still 25 joules. And I still have 125 joules of initial energy. Now when they stuck together, we lost energy. So there is this easy thought to have that when they don't stick together, we must keep our energy. Let's see what happens. Okay, this first one, 4 times 8 is 32, times a half is 16. That's 16 joules. It's not looking good. 49 times 1, that's 49 joules. 50, 65 joules. We still lost energy. We actually lost a lot of energy still. We have a change in energy of negative 60 joules. This is still, despite the fact that they didn't stick together, this is still an inelastic collision. Is it possible to have a collision where the energy is conserved? Well, let's look at that. If the energy is going to be conserved, now I'm going to work ahead just a little bit. Here's my 8 kilograms. Here's my 5 meters per second. 2 kilograms. 5 meters per second to the left. We're still calling to the right. Positive. We still know that our initial momentum, we haven't changed any of these things, so that's still going to be 30 kilogram meters per second. We still know that our initial kinetic energy is 125 joules. Afterwards, so let's see what happens here. If mass 1 is going to end up moving maybe at 1 meter per second, mass 2 is definitely going to have to move to the right, and we can figure that part out again. Right? My final momentum is going to be 8 times 1, that's 8 kilogram meters per second, plus 2 kilograms times V2, so my V2, 30 minus 8 is 22, 22 equals 2 times V2, V2 is 11 meters per second. Let's look at what happened to our energy. We're going to have here a half of 8 times 1 meter per second squared, a half of 2 times 11 meters per second squared. 8 times a half is 4 times 1 squared, that's 4 joules. A half times 2, that's 1, times 11 squared is 121. So we have 125 joules. I did not lose any energy. My delta E is 0, and that makes this an elastic collision. So then what do we have? We have, if these things stick together, then that is definitely going to be an inelastic collision. We are definitely losing energy. Maybe I'll write it this way. If they stick together, we are definitely inelastic, definitely not inelastic. If they bounce off each other, we could be inelastic, we could be elastic. So sometimes it's easy to get this notion in your head of, well, if they stick together, it's inelastic, and if they bounce off each other, it's elastic, which is not true, unfortunately. Half of it's true. If they stick together, it's most definitely inelastic. If they bounce off each other, it could be either one. So then the question becomes, out of these two, how do you know? Well, if you've got two objects that completely retain their shape or bounce back to exactly what their shape was before the collision, then you're going to have an elastic collision. If you've ever seen a golf ball hit a wall, when the golf ball comes in, it's completely round. That's what golf balls do. But when it hits the wall, it like pancakes out. And flattens. And then it bounces back off. The golf ball doesn't go back to exactly its same shape, but it's really close. You wouldn't be able to tell the difference by looking at it if you got out careful instruments to measure. You would find that it has deformed just a little bit permanently. So that collision won't be perfectly elastic, but it'll be close. Our percentage of energy loss is going to be really, really small. If you have a piece of clay and you throw it at the wall, then even if it bounces off the wall, that clay is not going to be the same shape as it was before it hit. That one's going to be very inelastic. We're going to have a percent energy loss that's pretty high. I will link a video of this golf ball hitting the wall because it's an interesting thing to see. But that's the idea of elastic versus inelastic collisions.